So I've got this massive tanker boat, and I'm going to try to accelerate it from rest using two jet engines. Powerful jet engines. Well, jet engines are powerful enough to make an airplane accelerate to takeoff speed, but the tremendous mass of a tanker means that the acceleration here is going to be small. So here's what I'm going to do. I have this force F that I'm giving. I'm going to double that force because I have two engines that I'm going to strap onto this tanker. So according to Newton's second law, F is equal to ma. So here I have twice the force is equal to the mass times the acceleration. So if I rearrange that, the acceleration of the tanker is going to be equal to twice the force of one jet engine divided by the mass. When I get that acceleration, it'll be small indeed, particularly compared to the very large mass of the tanker. If I want to know how much time it takes for this tanker to get up to speed, I'm going to use a kinematics equation, v is equal to v naught plus at, where the initial velocity of the tanker is equal to 0. It's starting from rest. I just found the acceleration, so I can find the time by taking the final speed, whatever it is in your version of the problem, and dividing by the acceleration. That will get me the time in seconds. Be careful, because the question itself is asking for the time in hours, so you'll have to convert. But since there are 3,600 seconds in 1 hour, that unit conversion shouldn't be too much of a bother. The next problem I have is this kid sitting in a wagon, and someone pulls the wagon with a particular amount of force, and I don't know how much. I don't even know the mass of the wagon. But what I do know is that Newton's second law is true. F is equal to ma. So if F is equal to ma, this is m times the accelerations given. Now, in the version that I looked at, the acceleration was 1.4 meters per second squared, which means the force that the person exerts is equal to the mass times 1.4. Here's the thing. That person exerts the same force to pull the wagon plus a kid in the wagon, where I'm told that the mass of the kid is 3 times the mass of the wagon. So the total mass now is the mass of a kid, m, plus, or mass of the wagon, pardon me, plus 3 times the mass of the wagon. That's 4 times the mass of the wagon. Same force. So the force is equal to 4 times the mass of the wagon times whatever the new acceleration is. That same force was 1.4 times the mass. So I can write this as one equation. Force is equal to force. On the right-hand side, I write 1.4 m, because the force is equal to 1.4 m. But on the left-hand side, I also write that the force is equal to 4 times m times a new, the new acceleration. Since I have the unknown mass on either side of the equation, I cancel the masses, and I find that the new acceleration is the old acceleration, 1.4 meters per second squared, divided by 4. It's kind of fun that I found the new acceleration without ever knowing the force or the mass of the wagon at all. Here I have a very similar problem to solve. Reminds me a lot of the previous problem, the kid in the wagon. I have a car that's going to tow a car. So I have a car that can exert a certain amount of force to accelerate itself. I don't know how much force that is, and I don't even know the mass of the car. But I do know that the acceleration, in my case, 4.8 meters per second squared. So I can write that F is equal to m times 4.8 meters per second squared. The force, unknown. The mass, unknown. And in the second part of the problem, I'm told that the same car, that means the same force, can tow another car with a different acceleration. The other car has the same mass. So the new mass is 2m, and the force, therefore, is 2m times the new acceleration. Just as I did in the last problem, on the left-hand side, F is equal to m times the acceleration. On the, did I say left-hand side? Right-hand side. On the right-hand side, F is equal to m times the acceleration. And on the left-hand side, F is equal to 2m times the new acceleration. Solve for the new acceleration. I find it's 4.8 meters per second squared divided by 2 is 2.4 meters per second squared. Going over it like that, I feel like that it's almost identical to the preceding problem. So, yeah, now I've got this small car, and I'm going to jam a bunch of passengers into the car. And I'm doing Newton's second law, again, F equals ma, but this time they tell me that the mass of the car, and the driver, I suppose, is 1,100 kilograms, and that it can have an acceleration of 2 meters per second squared. Well, now I can calculate the force, mass times acceleration. That's 2,200 newtons of force that this car can exert. Now, same car, but I'm going to load it up with 400 kilograms of passengers. That's going to increase the mass of the car to 1,500 kilograms. Newton's second law again. F equals ma, so 2,200 newtons is equal to 1,500 kilograms times the new acceleration. I find the new acceleration by taking 2,200 newtons and dividing by 1,500 kilograms. This problem, a simpler problem, because I had more information to work with. Now I have a problem that's going to combine my Newton's second law with a little bit more kinematics. I have a car that's going to skid to a stop. Now, Newton's second law, F equals ma. I'm told that the force of the car skidding is 2,000 newtons. The mass of the car is 1,500 kilograms. And so I can find the acceleration of the skidding simply by taking the force and dividing by the mass. 7,000 newtons, 1,500 kilograms, divide, I get 4.7 meters per second squared. That acceleration is the acceleration of the car slowing down. I remember back to my kinematics that in order to slow down, a car with a positive acceleration would have to subtract velocity in every second. So that 4.7, I'm probably going to treat it as negative when I do some calculations with it. Now the question is, how far can the car go skidding to a stop? Well, I'm going to use a kinematics equation. V squared is equal to V naught squared plus 2a delta x, where the final velocity that appears on the left-hand side is 0, because the car is going to skid to a stop. A little bit of algebraic jiggery-pokery, and the displacement delta x is equal to negative the initial velocity squared, whatever your initial velocity is, 2 times the acceleration, whatever your acceleration worked out to be. Don't mind the negative sign, because the acceleration is negative. This displacement will work out positive in meters.